So, as you saw from the video, my fun, cool title is Shell of Survival. So, a brief introduction. My name is Nima Darafshi. Like Monica said, I'm a senior at Union College. I worked in the Marine Invasion Lab, so I worked a lot with looking at Erythropanopeus harisi, or white-fingered mud crabs for short, and also the parasitic relationship that loxoparasite have with these crabs as well. So these loxoparasites were first found within Chesapeake Bay in 1964. And if we look over on our top left image, this is a male mud crab that has a different apron or an abdomen, but within that apron, there are sexual reproductive organs that help all these crabs reproduce. On the bottom left, it is a female mud crab. They have a dome-like structure and a dome-like apron that people in the area call and refer to as the Washington as the Capitol building, the dome. The top left is a loxoparasite, and if you can see, especially from my video as well, these parasites can get very big, and they will occupy this different apron, and it can be as few as one to this top right, which are six different parasites. And it does differ compared to the bottom right, which are ovigerous crabs. Ovigerous crabs, and ovigerous is just a fancy way of saying egg-bearing crabs. And these are typically females that have tiny, small little eggs, similar to tapioca eggs, if anyone loves drinking boba. But they do differ in the appearance and also the occupying of the apron compared to the loxoparasites. And a quick brief about the parasites. These different types of loxos will infect the shells of these crabs. For instance, a mud crab is probably going to mold out of its shell and as it grows bigger and bigger, and that will typically leave these crabs more vulnerable and open to these infections. And not only do they occupy the abdomen and that flap right there, changing their physical shape, but that's also going to have a psychological impact on these crabs too. So as we saw with the infected ones and also the ovigerous crabs, they have their apron all occupied and filled up. Those female mud crabs are typically going to protect their apron and all those eggs, their feet, and more females who are infected and have those different types of parasites growing on them are going to behave compared to ovigerous and egg-bearing mud crabs. Another note as well, mud crabs especially are big burrowers. They live under oyster shells, under wooden debris, and also mud. They love seeking shelter. And that brings me to my big question. What impact does the loxoparasite have on white-fingered mud crabs' ability to seek shelter? And as stated in my hypothesis, if a crab is infected, it's going to have a different shelter-seeking time compared to non-infected crabs, but they will align more similarly with ovigerous or egg-bearing crab shelter-seeking times. And this is where I started to kick off my experiment. So I collected all of my crabs on August 1st and August 6th, and I decided to undergo experimentation on the 2nd and the 7th, just to give those crabs a bit of layover so they don't become very stressed and I'm not putting them in very high stress conditions that could impact their behavior. So I'm talking about very, very small mud crabs. The largest that I had was 18.39 millimeters in their carapace width that you can see from end to end. And for reference, 18.39 millimeters is slightly larger than the length of a dime. So we're talking about really, really small mud crabs. Oh, here we go. So in total, I collected 80 mud crabs in two different batches from August 2nd and August 6th. And I conducted 320 trials. Well, what does that mean? So I have a crab, which was a female, an infected male, an infected female, and an ovigerous crab. I tested them in normal seawater that I collected in the nearby river for the lab I was conducting in. And I tested them in the morning, in the AM, and the night, or the afternoon, the PM. I would test one crab in the seawater here, and then do the exact same thing for blue crab water. In this experiment, I would typically place the mud crab 50 centimeters right in the middle, where that yellow dot is on the tank, and I would want to time them to see how quick it took for these crabs to get to the oyster shell side. 5 minutes was going to be my cutoff, so they could have taken 10 minutes, they could have never gotten into those shells. But that's the one time I wanted to cut off and see uh, where I can be able to cap off my results and giving these small mud crabs a very fair shot. And this tank was filled with 3 liters of water. 3 liters was going to be for seawater. And when I was experimenting with blue crab water, that crab water was 2 liters of seawater and 1 liter of blue crab water. And you might be thinking, well, why am I going on and on about blue crabs and the blue crab water? Well, my seawater is my control experiment. That's the normal condition that these mud crabs are going to live in. The blue crab water, on the other hand, those big crabs are natural predators to these small, tiny, burrowing mud crabs. So that's one thing I really wanted to test to see what kind of stress it will have on these crabs and their ability to scurry away and seek shelter and safety under those oyster shells. And I was able to collect this blue crab water from the education center nearby and try to instantly test this water. Because if I held that water for too long, the smell and the scent from this blue crab is going to degrade, and it won't be as helpful for those mud crabs to pick up and understand that, oh, they might potentially be in danger. And then on to my results. So I had 90 trials in total out of my 320 that showed mud crabs capping off at 5 minutes, that they weren't able to get to the oyster shell side, and they weren't able to get there quick enough. Looking at the distribution, while it isn't as important to my question about what impact do parasites have to the crabs when they get to the shells, the breakdown right here I have is about 8 to 9, 6 to 8, 3 to 11, 5 to 4, 20, relatively close numbers. Ovigerous ones were the ones that seemed to burrow away and take a lot longer. But I wanted to get into the more nitty gritty. Right here, I wanted to just first off test my timing and my results conducting my experiments in the morning and the afternoon. So on the left right here, I have seawater, and this is going to be testing the bottom left, the morning data, and then the bottom right, the afternoon data. My y-axis is the amount of time taken to get to those shells in seconds. So the highest amount is 300 seconds, which is 5 minutes, and the lowest amount would be 0 seconds, but that wouldn't be possible. So looking at these two different types of data, there isn't too much data when I'm collecting my results. There is probably similar timing. As you can see in the seawater, there's a difference of 19 seconds. In blue crab water, there is just a difference of 9 seconds from their mean average, or where the X is on the dot. So I took that into consideration and thought morning, afternoon doesn't have an impact on the parasite and the crab's ability to get to these different types of oyster shells. And this is where I wanted to do an individual breakdown. So I have males and females, and then I categorized all those males and females into not infected males and also infected males and females. Looking at this, there wasn't too much of a disparity either in my results. I have an average mean of 46 seconds to 39 for the seawater on the left graph, and the right graph is 71 to 83. Not too much of a difference. And now I'm just trying to work and funnel my way down to the nitty gritty. Just looking at all of them compared to non-infected infected, that's not great results. So I decided here to break down all of my data, looking at all the males compared to the ovigerous egg-bearing crabs. We have the non-infected and the infected males on the left side, and the ovigerous crabs on the right side. So looking at my left graph, the seawater, there's about 6 seconds of a difference from non-infected to infected, and then 15 seconds from non-infected to ovigerous. Not too much disparity. But when I look at the blue crab time, there is a difference of about 15 and 25 seconds from non-infected to infected, and then the jump of average time from 88 to 132 seconds is just under 50. So I'm observing that a lot of ovigerous crabs are taking a lot longer to get to the shells compared to non-infected and infected mud crabs for the males. And now we're going to head over to the females. This shows even closer results for the seawater on the left graph, that there is a normally faster time that it takes for these female crabs to get to the shells. And the difference is about 27 from the non-infected to the ovigerous females. But then moving on to the right side, where I'm testing the stressful means are almost identical, and the difference is about 52 for the ovigerous female crabs. So those ovigerous crabs are a lot more slower compared to all the non-infected and infected females in stressful water conditions. And this brings me back to my original question and my original hypothesis. So what impact do the loxoparasite have on white-fingered mud crabs and their ability to seek shelter? Well, I saw that through my data that both infected males and females were quicker to reach the oyster shell shelter than the ovigerous and egg-bearing females. Additionally, those not only were they quicker, they also had similar times for the males and females when it took them to reach the shelter too. And looking back on my hypothesis, that essentially disproves it. I was looking at and thinking that a parasitic male and female, because of their psychological and physical change, would have similar to the ovigerous crabs and sheep. And then on top of that, with distinguishing it between seawater and blue crab water, I thought to myself, blue crab is really stressful, a high-end environment that is going to force these crabs to get to shelter as quick as they can. Looking at all of my data, and I see that there are more prolonged times for blue crab water compared to seawater across all spectrums, I saw that the blue crab water was slowing down these shelter seeking times. And I have a few understandings and assumptions for that. In my tank that we saw, there was a clear end, and then there was also just one end that had oyster shells in it. If a mud crab is going to run around and do everything it can to find shelter and figure out where is this blue crab that I'm sensing, and it doesn't see on the open end, it might assume that it's going to be on the shelter side, on the oyster shell side. And because of that, it will be a lot more hesitant to walk over to those areas and take a lot longer for them to find and seek that shelter. That's all I have for my presentation. I wanted to thank Colette Gerard because without her, I wouldn't have this opportunity funded for me to take advantage of all the resources that Smithsonian has and be able to complete this scientific project. I want to thank Monica Noble and also Chris McMahon. They were both my advisors who helped so much in order to give me so much feedback based on the experimentation process, my hypothesis, my methods, my data especially. And on top of that, I want to also thank Cirque too. Cirque was very helpful for me to use the labs, the wet labs, the blue crab water that I needed to conduct my experiments. But that's all I have for me. I want to also thank you all and open it up to questions, comments, and concerns.
Thank you, Nima. Yeah, Chloe, please go ahead. Oh, you're muted still.
Thank you, Nima. That was really, really interesting. I learned a lot. I have a question.
Yes.
And I'm not a scientist, and I'm not sure I can ask the question correctly. But did you consider that the crabs with the eggs were heavier? In other words, the crab had to carry the egg sac, and I don't know how heavy the egg sac is in relation to the crab, but maybe that's one reason that the egg carrying crabs were slower in getting to the shelter, the oyster shells. And I don't know what percentage of the total crab weight is represented by the egg sac, and whether the egg sac is something that slows the crab down, not only because of the weight, but also because of the friction against the aquarium. Does that make sense, my questions? Or
Yes, I'll have Monica jump in if she also has further insight on this. But no, I never weighed the crabs as well, because weighing the eggs and also weighing the parasite as well might be a little bit difficult across the carapace width size. But I think one reason I didn't want to include that was because it's a lot of data. I don't think I have enough time for this summer to complete that. But on top of that, some of the infected crabs that had those parasites could have significantly more eggs or a significantly larger parasite size compared to the amount of eggs a mama crab would have. While I did try to pick a lot more mature crabs that had very mature parasites attached to them that they're exposing outside of their apron, I think that could be a good experiment for somebody else who would want to do it. However, the size and the friction, I don't think would be the number one thing to consider. And my aspect in experimentation I wanted to look at and question more specifically is that psychological impact as well.
Thank you.
No problem.
I like this idea of the psychology of the little crabs.
Yeah.
Are there any other questions for Nima? Yeah, Monica.
What changes in behavior did you see between the crabs when you added the blue crab water? What did they do if they didn't run to the shell? And what were
Yes.
the ovigerous crabs doing that was different than the parasitized crabs?
Yes, while I collected this data, it was difficult for me to try to graph this down and exemplify it, but I had a extra notes section. What I did find to be very common with many crabs who took a lot longer is that when I placed them in the middle, they would instantly scurry to the side, or more likely than not, they would end up in the opposite side of the tank in the corner. And with female crabs as well, they have a tendency to want to protect those eggs, and they'll typically fidget around their claws. They want to tuck in their feet as well, make sure they find as much shelter as possible. With the blue crab water as well, something I saw a lot more with the blue crab water compared to seawater was a lot of mouth moving. And what that is essentially telling of a crab is that it's breathing. So it is picking up on a lot of the blue crab scent. And in blue crab water, it's going to smell a lot more and try to figure out and use different types of smelling and sights to figure out where that blue crab is, and also simultaneously be reserved as much as possible. Those are the different behaviors, like qualitative behaviors rather than the quantitative behaviors that I found within these crabs too.
All right, any other questions for Nima? Okay, thank you very much to both Crystal and Nima. I enjoyed your talks. It was lovely to get to know you some this summer, and thanks to everybody else who showed up. I know we've had lots of intern talks this summer. They've mostly been amazing, so I really appreciate all of you showing up to support the interns, and we'll do it again next year. Thanks, everybody.
Thank you so much.